waves, A and B coefficients, and cosmological constant. All the three are Einstein's contribution. This year is also 47th year of moon landing of Apollo space mission. I would like to introduce Mr. Sivaram starting from that point, because when the moon mission was going on both in Russia and America, as a young boy of 16 years, yes, Sivaram was a young boy of 16 years, he had sent calculations for the landing of the moon to NASA. NASA had calculations, it has sent the prize and also the congratulation letter to Mr. Sivaram. You would have seen any number of articles on astronomy and astrophysics related popular science articles in Deccan. So the articles will be very rich. Most of the articles are written by Professor Sivaram. If it is on astrophysics, high energy particle physics, something like that. So this is at the outset, the brief introduction of Sivaram as a person of mass. He is also the person of class. He is both mass and class. He is basically a physicist from Indian Institute of Astrophysics. He obtained his PhD from Indian Institute of Science in 1977, and after a few years of working at IASC, he moves on to various other institutes. The first one is Indian Institute of Astrophysics. His early work on the early universe resulted in some of the earliest work on inflation models dealing with a time-varying cosmological constant. This is something very slightly, it has a gravity for the public, but what I can say is, as far as the Big Bang theory is considered, the first we say the universe inflated and then it has, the Big Bang has taken place. So he has worked on that inflation theory. If you go through his CV, it is very rich and very strong. So that I take out most of his work are in the area of high energy particle physics and related to aspects of universe and other things. So over the past few years, he had collaborated extensively with leading scientists from several countries. He has held more than 10 visiting professorships abroad, including 2 sabbaticals. Over the past decade, in the universities of Europe, North and South America, Australia, Russia, etc. He was also the joint director of projects of the World Laboratory in Geneva for a period between 1989 to 1994. His recent foreign collaborations include work on chromogravity approach to quark, gluon, confinement with Nobel laureate Professor Abdul Salam and others. So he has, like this, he has worked with a lot of people of highest caliber, that are the Nobel laureates and other scientists. Of course, awards follow the hard work. There are many awards. The mentionable ones are Martin Foster Gold Medal and Ettore Majorana Fellowship. The Martin Foster Gold Medal is always given by Indian Institute of Science. It is given in once in 5 years for the best thesis of that year. That means his PhD thesis was one of the best in the 5 years of IHD PhD thesis. He is also a fellow of International Astronomical Union and a member of IAU Commission on various other platforms he has worked. He has of course written quite a good number of books, of which the popular ones are Introduction to Astrobiology, University Press publication, Rocket Dynamics and Space Travel by World Scientific, Modern Astronomy, Startling Facts, and other books. He has written 2 more books beyond that. He is a senior professor, chairman of Theoretical Astrophysics Group from 2001 in Indian Institute of Astrophysics. If the same biodata CV is expanded, it can be expanded for 10 to 15 pages. So that is the richness of CV. He has number of records set in his name. There are about 21 records. If I keep reading, it takes another 15-20 minutes. But if I read one or two, so most papers written during the first year of visiting scientist position at Indian Institute of Astrophysics. In 1 year of 1981, he has written 14 papers, 12 in leading journals, 2 in international conferences, 3 courses taught, 20 lectures on various topics, 3 public lectures, so announced in newspaper and other things. Okay, this information is announced. Coming to the other things, between 91 and 96, 9 visiting professorships held abroad, including 2 sabbaticals. 91 and 96 again, 35 lectures given in foreign institutes and universities. Like this, we have, he has won prize for single author prize in the international platforms. He has written papers with the Nobel laureates and astronomers, royal citations from 4 Nobel laureates and other things are to his credit. Mr. Sivaram is a person of both class and mass. So every year, almost every year, he is coming to Bangalore Science Forum, delivering lecture on the various topics related to either high energy particle physics or astronomy or universe. So this year, we have him to deliver the lecture on Centenary of Einstein's Trilogy, Gravitational waves, AD coefficients and Cosmological constant. It will be rich. So I expect you to get energized to receive the information. Now, propose a warm welcome to Mr. Sivaram on behalf of all of us here.
So let me come to today's topic. So you see the Centenary Einstein trilogy. So what's the trilogy? 3 things, Trilogy is of course quite a common thing. We have got in more mundane context, we have the Lord of the Rings trilogy. Okay, that again, the Hobbit's trilogy, so many things are there. And you might have heard of the writer Einstein popular who died recently. Took a talk, one of his great books. And I read that when I was in ISC as a student. And that again is a trilogy. Trilogy means 3 things. And so these are famous trilogies. And of course, you might have heard of the author Stephen King. He also writes trilogies, the Dark trilogy and so on. It's Stephen King, not Stephen Hawking. Okay. The difference between only the Haw is missing. And Stephen King is a well-known author, very best-selling author. As far as literature is concerned, he is far more prolific than Stephen Hawking. Although Hawking, because of his brief history of time, also became a best-selling author, apart from being a great physicist. Okay, so let me come to this Einstein trilogy. So in the year, see, as you know, 2005 was celebrated as the year of physics. And see, that time it was a celebration of Einstein's classic 4 great papers, which thoroughly shook physics. The theory of relativity, equity, Brownian motion, photoelectric effect. That's a great year for Einstein. Okay? And he happened to be unemployed. He was working the patent office, not even working in physics. So that was a very big achievement. And he didn't stop with that. He continued with the. Only 5 years later he got a job in the first place after a job in physics, in spite of the 4 great papers. And then he continued with his work in physics. And it turns out that 1916 can be called another, as we shall see, another year of miracles. That 1905 keeps us as the age of miracles, the year of miracles. We got here 4 great papers. And it turns out even in 1916-17, when he was already, older, 10 years older, he still had another year of miracles. So these are the 3 topics we are going to address today. So what are these 3 topics? And so I'll take up came in the year 1916-17. Okay, followed one after the other. So, so we'll see what and gravitational waves. Quite recently, a lot of fanfare has been there. You know, very much big announcement was made in February of a discovery made actually in September of last year. First time gravitational waves are actually being detected. Okay, no, in a direct evidence, and two great, very costly detectors, the LIGO, in both in the US. Okay. And so this was predicted by Einstein 100 years back in 1916. It's the 100th year of prediction, and it took 100 years to verify. Okay, directly. So you see, that's a very big discovery. If Einstein were here, he would have got an Nobel Prize for gravitational waves, and very important. And of course, the next is the A and B coefficients. That A and B coefficients are very, actually it was Einstein's quantum theory of radiation which introduced in 1916. He wanted to know how photons interact with matter and systems. So he introduced his coefficients. He introduced a new concept called stimulated emission or induced emission. And was trying to derive the Planck law of radiation, okay, which Planck had done some couple of years back. And so why did this become important? So Einstein's goal was quite modest. He wanted to understand Planck's law and derive it from more basic principles. But then the A and B coefficients, especially the stimulated emission, played a very important role later in developing lasers and lasers. Okay, it's because of stimulated emission that lasers and lasers work. You excite a particular number of electrons to a higher energy level and may induce them to literally induce them by passing electromagnetic wave of the right frequency. You induce them to emit all at once their radiation. This is stimulated emission. So you get a coherent, very powerful beam, the laser beam. Of course, Einstein could not have imagined those things. He had no such idea because he even didn't understand much about radiation. That work that photons, that is quantum radiation, require a new statistics came with the work of Bose later, 10 years later. So Bose in 1924, who first suggested that photons obey a different statistics apart from the Maxwell-Boltzmann statistics. So actually Einstein himself realized that photons, being bosons, can all occupy one state, a single state, and this is in fact the basic concept of the laser. Can have all the photons marching in static. Okay. So this was again another seminal contribution of Einstein in 1926, 10 years after this, the Bose-Einstein condensation, which was verified in 1995 experiment. So Einstein had a lot of other things to do apart from the relativity theory. So A and B coefficients we see are again very similar and important. And the last one is the cosmological constant. We'll see that, and that was actually he said it was a big blunder. It was a big blunder, but then it turns out now in cosmology that maybe the thing which is the most important, the universe. Okay, so we shall see these three very important developments. That's why I call it the trilogy. It is 100 years since he proposed these three similar ideas. 100 years since he proposed these very similar ideas. That's why I call it the trilogy. Come to gravitational waves now, the first topic. So brief account of gravitational waves because there is a lot of excitement about the direct effects of gravitation. So what are gravitational waves? You all know electromagnetic waves, whenever an electron is accelerated or the charge particle is accelerated, you should get electromagnetic waves. Similarly, when a mass plays the role of charge in gravitation. Okay, mass is because the Newton's law, the product of the masses gives the force. So you got steady mass which is accelerated, okay, so should give rise to gravitational radiation, and by analogy with electromagnetism. So Einstein predicted that masses in acceleration should, say, one body going around another, okay, two bodies going around each other, or a vibrating bar, they should all emit gravitational waves. Okay. So it's different from electromagnetic waves because the why is different. Velocity is also that of light, okay, and however the lowest order is quadruple. Because in electromagnetism we all study dipole radiation, lowest order is dipole. Just as the sky is blue, by the way, the Rayleigh scattering, it gives a typical 4th power a blue light is scattered. Okay. So you got because the lowest order is dipole range. But gravitation is see the lowest order is quadrupole, so it's much weaker for that account. And also there's no dipole gravitational radiation, and the strength of the gravitational interaction is much weaker. The electromagnetic interaction between say 2 protons or 2 electrons is some 10 to the 38 or 10 to the 40 times bigger, okay, than the gravitational interaction. So it's much weaker. The extra gravitational radiation will be much weaker because the lowest order is quadrupole and the much weaker interaction. That's why it has taken so long. Maxwell predicted electromagnetic waves of his electromagnetic theory. Within 10 years, English hertz had already generated and detected the waves. Okay. Then of course the rest is history. We make ubiquitous use of electromagnetic waves everywhere, okay, including the internet, everywhere, mobile, everywhere we use electromagnetic waves. But gravitation, because much weaker, it has taken now 1 century to verify the image. Okay. That's why it has taken so long, because much bigger detectors. That's the reason. Why does monopole? There's no monopole electromagnetic radiation, there's no monopole gravitational radiation. I think I believe some students of physics may be there, they may like to understand this. So monopole radiation vanishes in both cases because of conservation of charge and mass. So this tells you that sigma E equal to 0, the total charge is conserved. So sigma E dot, that is the rate of change of charge in time is constant, is 0. So there cannot be any to get radiation because there's some quantity changing, something vibrating or something changing in time. So charge and mass are both conserved, they don't change in time. So you don't have monopole radiation. For electromagnetic waves, dipole is the lowest order. For gravity, dipole vanishes because of conservation of momentum. In addition, dipole comes because of your product of, suppose you've got two charges, E and E at either end, and X is the separation. Dipole moment is given by E into X. Okay. And in the case of gravitation, we M into X. But then, to get the radiation, you must go to the time derivative, double time derivative. So mx double dot is nothing but force. Force is rate of change of momentum by Newton's law according to Newton's law, and momentum is conserved, so that's the branch. So that's why gravitational dipole radiation vanishes. For electromagnetic radiation, Ex double dot is not 0, it's not related to the momentum. That's why you get the blues, the sky lightning, bloom and things like that. Okay, the force, like a force, the frequency force. But gravitational dipole radiation also vanishes because of the conservation of momentum. Lowest order is quadrupole, so it goes to the 6th power of the frequency, not to the 4th power. So I just, in fact, there's a lot of excitement and fanfare a couple of months back. You would have seen all over the media, everywhere. And gravitational waves at last being discovered. Okay, very big discovery. Also, some Indians were also involved. There are 1,005 authors in the paper. So it's a real international team effort. Okay. And if people are talking about Nobel Prize, only 3 can get at a time. Only 3 can get. So you can see who the 3 are. The 3 who pioneered. One is Kip Thorne, Trevor from Scotland, and another is Rees from MIT. So these are 3 people who first registered will get. All 1,005 can't be given. Similarly, in the large particle physics experiment that Rees goes on, 600 authors per day. So only the person who proposed it was on that 6th one. So that's what usually happens. So you need a huge team effort nowadays. This is called big science. A lot of investment is required to verify some of these things, because they are very weak effects. The interactions are very weak. So we need a very big detector to detect these things. Part of these science. And so although only now it has been confirmed direct detection, Weber, you might have this picture here, Dr. Joseph Weber, he was the first pioneer the detection of gravitational waves. In fact, he wrote a book on gravitational waves. As students, we read it. In fact, Madam referred to my interest, obsession with rocket dynamics. That time itself I was interested in gravitational waves. I read Weber's book. So he already had so Weber already had a bar, okay, a bar antenna. It's called a small wire. The gravitational wave, what it will do, it will make the bar contract up and extend sideways and contract up and down. Okay, this is because gravitational wave part of it distorts the bar. So you will have by a very small amount, 1,000th of the diameter of the proton. So Weber had a very complicated apparatus to measure the small displacement of the bar due to the passage of the gravitational wave. we had the piezoelectric, very sensitive piezoelectric detector and things like that. We take a long lecture to describe his achievements. So, unfortunately, he was so eager, so enthusiastic, he thought he had detected gravitational waves. Right? In 1969 or so, he thought he had detected gravitational waves from the center of the galaxy. That time was a lot of publicity was there. But unfortunately, there was only one detector that time. No other competitive detectors were there. The thing is, that's why now with the LIGO, we have two detectors in the US. Both simultaneously, detect the signal. So if you have only one detector, these instruments are very sensitive. Even a passing train or a small seismic shock, earthquakes are happening all the time, very small shifts of the cluster, or even a train passing by or a plane flying overhead can, or even depending on the sensitivity, even the loaded lorry can cause power displacement. So there should be two detectors finely separated apart to signal it's a really celestial event. So to identify the really celestial event. That's why this LIGO, we'll come to that, the Laser Interferometer Gravitational Observatory, is to be located in 5 different continents. Right now only 2 are there, both in North America. Actually, the one supposed to be in Germany, one in Italy, Virgo, the Japanese Tama, and one was to be located in Australia, but the was not agreed to by the government. So India has probably taken over the thing. So the thing is, for all these 5 detectors in different continents simultaneously see, coincidence detection, then we know it's a truly celestial event. So you can pinpoint when it happened. So that is it. So unfortunately, Weber, what happened was after some time, they said he hasn't discovered. It was probably not, it gave too much of an energy for the radiation. So people thought that it may not be, there's no further proof. So he was quite disappointed. I heard Weber in a number of conferences. He was trying more and harder to have better and better apparatus. Okay. And he was almost quite unhappy that nobody believed. Okay. But then he was the real precursor because that inspired many other people to develop more sensitive devices. Okay. So the real precursor. And so Weber was a real pioneer in this, that's why his picture is there. He recognized as a pioneer of gravitational waves. Although there was a first step in trying to understand the phenomena, devise a detector, design the detectors. So this was a very important work of Weber. Okay. Picture there. I told you that a rod spinning can generate gravitational waves, but because the interaction is so weak, the force between any two objects is very, very low, ordinary. You need a very massive object to have a substantial force. For a rod 1 meter long, say spinning close to breaking speed, the power is only 10 to the minus 32 watts. Okay? So it's difficult to generate gravitational waves with the rack. It's not like Hertz, who generated electromagnetic waves very soon after Maxwell predicted and detected them. And Marconi soon sent the signal across the Atlantic. So electromagnetic waves became general use. But for gravitational waves, it's so difficult to generate gravitational waves in the lab. There's no Hertz expression so far. Even for the Earth-Sun system, the gravitational wave, because Earth going around the Sun can generate only a few watts. For Jupiter going around the Sun is 200 watts. So it's a very, very, very weak effect. But fortunately, we have got much more massive objects in the universe, the pulsars. These are objects which are exhausted, they are stars which are exhausted their nuclear field. They are collapsed into what are called neutron stars. Okay. They are so dense that this much material will weigh 1 billion tons. Very highly compressed. So there are 2 neutron stars going around each other. This is called a binary pulsar. Binary. Most stars form binaries. In fact, the sun is a rare example of an isolated star. Okay. So even these pulsars form binaries. So the binary 2 neutron stars going around each other. So this is the first example of a binary pulsar. TSR means pulsar. 1930 plus 16, that is the designation of the thing. And the velocity was 300 kilometers per second. The period was 8 hours. Okay, the period of orbit was 8 hours. So this is the formula which Einstein gave. Great formula which Einstein gave, m square r4 omega 6. He gave this around 1960, the same time. Eddington somewhat corrected it, so it's called the Einstein-Eddington formula. So the orbital period, so actually we are able to see the effect in the bandwidth pulsar. Because the system is dissipating gravitational energy, so they are coming closer. They are losing energy, they are coming closer, and the orbital period slows down by 76 microseconds every year. And this is a strong indirect evidence because pulsars can be monitored because of the radio emission, they can monitor very accurately. A small change in the period can be measured. So this was actually measured by Hulse and Taylor over a period of 20 years and strongly confirmed the Einstein's prediction of gravitational wave, but indirectly. So much so that Hulse and Taylor got the Nobel Prize in 1993 for monitoring this pulsar for 20 years and verifying that it generates gravitational waves indirectly. They verified this Einstein formula to about 1%. The agreement less than the agreement with theory is about 0.1%. Okay. So now they found another binary pulsar some years ago. They're 2.4 of them. They are very close to each other, and they approach each other a few meters a month. You can actually see them approaching each other. And there's a very big change in the perihelion per year. You all might have heard that Mercury's perihelion shifts by 43 arc-seconds per year, one of the predictions of Einstein's theory. But here the effect is so much larger, 16 degrees per year. Okay. So this is an example of a testing ground for Einstein's theory. And now the agreement between theory and experiment is 0.1%. So even before the direct detection of gravitational waves, we already detected indirectly. Okay. And two people already got another prize, Hulse and Taylor, for this very nice verification. So now the excitement is they are directly detected gravitational waves with an instrument. Okay. Another example is OJ287. There are two black holes, binary black holes. Black holes are collapsed objects on which no light also comes out. They are so gravitational field is so strong, and they can generate something like 10 to the 40 watts, okay, of gravitational power, and comparable to the electromagnetic radiation. And the Mercury, and this is another system which is being monitored. And there are two huge black holes. One weighs 8 million solar mass, times the mass of the sun. Another 100 million times the mass of the sun. They're going around each other in 12 years, period of 12 years. And of course, the binary pulsar is supposed to merge. The two neutron stars are coming closer and closer. They collide in another maybe about 100,000 years or so. In that case, the intense burst of gravitational radiation will change the length of any part, like Weber's bar, by 1 part in 10 to the 17. Of course, we'll have to wait for a long time for this to happen. Okay. Anyway, we are indirectly detected all the gravitational waves. So, the universe is full of these kind of objects. Okay. So, we expect many more events in this kind of detector. Okay. So, we come to the how is gravitational wave measurable? So far I've been telling you about the theory and how Einstein and others developed the theory. But here we have about actual measurement. How is gravitational wave measured? So we got something like a Michelson interferometer. So we got this laser beam here. We got a movable mirror, a fixed mirror. So what happens is we have beam moving along parallel and perpendicular direction like the Michelson interferometer. So the passing gravitational wave can alter the distance the ray moves. Okay, like a bar, slightly shrunk and expand. Like that, the path of the light beam is slightly reduced and slightly extended. So what will happen? There will be a phase shift between these two. Like in the Michelson experiment, they try to look for the Earth's motion to lead that. Okay, so see a phase shift. So here again, a similar thing is that we got two light beams going in perpendicular directions, parallel perpendicular directions. If the passing gravitational wave is there is a small change in the phase shift that can be measured. Okay. So even a shift of 1 part in say 10 to the 20 can be measured. Okay. So that's why the arm of the interferometer is some kilometers long. We'll come to the next. See the optical path length. This is the test interferometer. Optical path length of 10 meters, round trip time of 3 minus 8. So you can measure a difference in time of 1 part in 10 to the 10. So the sensitivity is 1 part in 10 to the 17. Okay. So this is actually the instrument, the LIGO, which was used. So you got these two arms. Arms are 4 kilometers long. So only is very long, and the light beam is reflected back and forth between mirrors. So the path length is very long. You see, the path length is very long. You got back and forth between so 4 kilometers long. So several times we are reflecting the back and forth. So the effective path length is very long. So any small change in the path length can be measured. Any small change in the path length can be measured. Okay. We got test mark here, we got a photo detector here, interferometer detectors. So this can measure a distance of change of 1 part in 10 to the 20 due to a passing gravity. It can be from anywhere, from any part of the sky is passing by. It can slightly change the phase shift. Okay. That's what it does. So laser interferometer gravitational observatory LIGO. On February 11th, okay, of this year, the LIGO group announced the landmark discovery of the first detection of So the waves came from two black holes circling closer and closer to each other till they finally collided and coalesced. Most of the radiation was released in the final orbit at a period of 1 millisecond. The orbital period of 1 millisecond. The waves at a frequency from 0.6 to 1.2 kilohertz, typical of such a event. A final black hole and another 60 solar masses. 3 solar masses were converted to energy of gravitational waves. So peak power was 10 to the 51 watts. So the event took place 1 billion light years away. But still, because the energy generated was so large, the flux was measurable with the LIGO. Okay. So they saw this event. Actually, LIGO went into operation around 2002. They didn't see anything for so many years. Then it was upgraded in 2014. It was closed down for about 2 years. Then after it was upgraded, the laser power was increased. It was started detecting, made this first detection. And they also now had a second detection recently. So there have been 2 events already now. Okay. So what is the sensitivity? It's limited by several main noise sources. I told you even the instrument noise can give a false signal. So we'll be very careful to separate out. Before announcing, they have to be very careful. Although they made the discovery in September, they waited till February to announce it. Okay, they took a long time. So the thermal noise, again, so many things, statistical errors, merging neutrons are called the Virgo clusters they can detect. So all these technicalities are there. It will call for a lecture by itself, so I won't go into the details. So you can see that a lot of technology is involved, and of course now they are more ambitious. They want to go into space. There are a lot of problems with detectors on the Earth because Earth movements, I told you, can cause results which are maybe some spurious results can be there due to Earth's, due to seismic events, tectonic events, and so many other things. And Earth, there are a lot of noises made by artificial noises are there, vehicles, planes, so many things can alter. Okay, underground, the water, so many things, floods, so many things can change. But in space, it's free from all this noise. That's why it was suggested you have the laser interferometer space antenna LISA. So again, it's a trio. See, trio spacecraft, 3 spacecraft, each 2.2 meter diameter. Laser beam aligned across 6 kilometers. So small changes in distances can be measured. So this is the LISA. So this is the 3 spacecraft. Okay, it will be following the Earth's orbit. So each they are separated by 5 million kilometers in an equilateral triangle. Okay. So we got these 3 things. They will be monitored very precisely. Any small change in the distance of the spacecraft is maybe due to a passing gravitation. Okay. So it's sensitive to 1 part in 10 to the 27. So we can detect very weak sources very far. So this is an ambitious thing. Not likely to take off before 2030. I think the Americans cancelled the thing because they thought it cannot be worth it. So they preferred some of the Jupiter probes. They have quite stringent kind of things where they give money for these things. But the Europeans have said they will go ahead. So the European LISA, E-LISA will be probably launched in 2032 or 2033. Chinese also have a plan now. They want to launch in 2032. The C-LISA, Chinese. So that will be probably less expensive, but they also want to launch. This is still quite far away, these space gravitational detectors. So what exactly the little bit of the physics for upon impact of a gravitational wave, it will cause any detector to have quadrupole oscillations. In fact, each one of us can be a detector. The length can be stretched by the diameter of a nucleus and the passing gravitational wave. Very small. The Earth as a whole is stretch and expand by 1 nanometer. Okay, very, very small. Okay. So extremely small. So this is the formula for the change in length. Okay. So you can see it depends on the power in the gravitational wave and other things. So the velocity of light to the power of isotopic factor that I won't go into the detail. Now let me come. So this is the end of gravitational waves. Okay. Because see, I have to compress 3 topics now, trilogy. So I have to divide my time equally. I will divide my time equally. So may not be so equal, but still let's come to the A and B coefficients. So I told you we come to an entirely different topic. This shows Einstein's great genius that in the same year he could pick up 3 entirely different topics. Each one a great contribution. So I think this really we should appreciate. Okay. And so the A and B coefficients are another very important contribution. Okay. And as I told you, it has to do with atomic transitions. We are trying to understand how exactly, of course, the theory was given by Bohr. A few years back, Niels Bohr explained how atoms emit radiation. Electron is excited by photon to high energy level, and then it drops back to the low energy level, emitting a photon. Radiation is produced. But how exactly this happens? How is the interaction between, how do you understand it, say, macroscopy, atomic system, and external radiation? So Einstein tried to understand this, and he wanted to give a general theory of interaction of radiation with matter. Okay, this is electromagnetic, nothing to do with gravitational waves. Okay, electromagnetic range. You want to understand how electromagnetic radiation interacts with matter. So he introduced 2 coefficients. He realized these are called the A and B. One thing is spontaneous. See, the atom electron is excited at a higher level. It spontaneously comes back to the lower level. Okay. So this is how much of your radiation from your tube light or from the sun. It can be random. Spontaneous is quite random. Nobody tells the electron when to emit. It is excited after some time it emits. It's quite a random kind of thing. Especially many electrons are random process. So it is a quite incoherent radiation like what we get from this bulb or from the sun or from a cactus. Okay. But then Einstein said there could be another kind of thing called induced radiation. Okay. Then what you can do is that an atom can absorb radiation of the right frequency. Suppose the frequency of the photon just happens to be the same as the difference energy level between the excited level and the lower level. Suppose the photon is of exactly the same frequency. The electron will tend to absorb it readily, be induced to absorb it. Then it will emit it after some time, so this will be induced emission. Okay. And induced emission depends on the intensity of the radiation supply by exciting. Okay. So this is the difference. So we introduce the concept of stimulated emission, induced or stimulated emission, and he set up a general balance between these two. So A coefficient is the one which is the spontaneous emission. The probability of spontaneous emission. These are probabilities, by the way, or transition probability, you can call them probabilities. What is the chance it will emit? And B is another, or the rate, you can say. A tells you so many, suppose A is 10 to the power 8. The transition will be 100 trillion per second. Okay, 10 to the 8 per second. Similarly for the B coefficient. It was evaluated for every system, every particular substance or particular molecule or atom. So this is the thing. And it is very clear in the next one. And of course, this is what happens. I told you it's important for the laser because you've got induced emission, and you can make all of them induce all the electrons to emit at the same time. Okay. So by having incoming radiation of the right frequency. So of course, Einstein never thought it will lead to a laser because he had no idea that photons can punch together. That idea came with Bose, that you can have bosons, the particles can all be in the same state. Just the idea came later. But then, he introduced this idea of stimulated emission. His idea was very modest, 10 Planck. So this came later, this idea for the laser electron. We see we got partially reflecting mirrors and fully reflected. Actually, the beam is amplified between 2 mirrors. It's kept oscillating back and forth between mirrors. As more and more electrons, excited electrons release their radiation, beam gets more and more powerful. Finally, it comes out as a very powerful collimated beam, parallel beam. That's how the laser works. So anyway, this explains how that kind of. So we got the first laser was the ruby red laser. We used the ruby crystal as the medium for amplifying the light radiation. Okay. So what are the A and B coefficients? The transition probabilities used to describe the rate at which photons are absorbed or emitted per atoms or ions. So an atom emits radiation if an electron makes a transition from a higher energy state to a lower energy state. They have to go into N. M is a higher energy level, N is a lower energy. The transition can be either spontaneous or induced by the presence of some external radiation. The rate of spontaneous emission is given by A. So A is called the Einstein coefficient of spontaneous emission. Okay. Remember, this was 1916, 100 years back. Okay. And P is the Einstein coefficient of induced emission. And Einstein showed that A and B are related by 8 pi nu q by C q B. U is the frequency of the transition, okay, the energy of the difference between the higher level and the lower level. So 8 pi h u by c to b. X is Planck's constant, c is the velocity of light, u is the frequency of the external radiation. So the concept of induced or stimulated emission of a photon by an atom in the presence of electromagnetic radiation. That was the new thing here. So an atom can become excited by absorption of a photon of the right frequency. Suppose you got a photon of the right frequency, En by h. H is Planck's constant, this gives you the frequency. And having become excited, the atom can emit a photon. Okay. Having become excited, can emit a photon. So rate of absorption equals the rate of induced emission, both rates being proportional to the density of photons of the incoming radiation. So the transition of the induced absorption or induced emission is proportional to the intensity of the incoming radiation. Unlike the case of spontaneous emission, which is independent of the incoming radiation, it is spontaneous random. Here it is induced, so it is very definitely, you can say, manipulated. You have the induced incoming radiation, it induces the emission activity in the atom. So the process of stimulated emission is essential for operation of lasers and lasers. It's important thing. So now you know lasers are very ubiquitously used. Even the laser pointer is there, that's what I'm using. So lasers are used everywhere in surgery, communication, holography, any application you can think of, welding, whatever you can think of, laser is used, propulsion, everywhere is used. But it would not have been possible without this concept of stimulated or induced emission. Einstein introduced for a very different purpose. So that's the significance of this discovery, of this very important concept. So quantum theory of radiation, this was what Einstein was generally. In fact, he wrote a series of papers, not one. Between 1916 and 17, he wrote a series of papers. Okay, I don't want to go into all the papers. Okay, not all of them matching with each other, but still, he had the ideas. Okay, and quantum theory, study of emission and absorption photon, the atom using quantum mechanics. Quantum mechanics was still in the infancy. Heisenberg had not given the uncertainty principle. Schrödinger had not given the equation. So Einstein was still trying to understand what was known as that time. And photons excited by emitted by atoms when a transition occurs from excited to ground state. This we already seen. If an atom is exposed to external radiation, a transition can occur from ground state to excited by absorption of photons. Excited atom can lose energy that is gained by stimulated emission. However, atom can also emit in the absence of external radiation by spontaneous emission. So spontaneous emission in the absence of external radiation, stimulated emission in the presence of external radiation. There are two different things. Okay. So this is the picture. Quantum theory initiated by Einstein as an extension of Planck's radiation law. Planck had already given the radiation law. Other people had also worked on that. So he was trying to understand it from first principles. Planck almost fudged his result. He put a -1, he get the right result. But people did not know how exactly it comes out. Einstein was trying to understand, deriving from first principles. He wanted to derive from thermodynamics and quantum principles. So that's what he was trying to understand. So he said, so suppose you got electrons there, M is the higher level, N is the lower level, okay? And the photon is exchanged, a photon is emitted if electron drops from M to N. So suppose Nm is the number of atoms in state M. The higher level you got Nm. So number of spontaneous emissions is per second is Nm into Amn. Amn is Einstein coefficient for M to N transition. Okay, for M to N transition, this is Einstein coefficient. Nm is the number of electrons in the M2 level. So the product gives you the number of spontaneous emissions. On the contrary, number of induced emissions is Nm into Bmn. B is the induced emission into epsilon. Now the energy density of the external radiation comes. Only if you got external radiation, you get stimulated emission. Okay. So this is the probability for stimulated emission. This is the number of transition of the stimulated emission. This is the number of transition of the spontaneous emission. Very simple, very simple analysis. So we can also have a transition from N to M. See, you can absorb, the electron can absorb the energy, those are the lower level, and then induce by external radiation. So number of absorptions you can find out. So number of absorption will be n into d n. Now the Einstein D coefficient comes. While the spontaneous emission is incoherent, I told you it's incoherent, random, the induced radiation, stimulated radiation, has same phase as the external radiation. So the induced radiation has the same phase as the external radiation. It's coherent. That's why it can be amplified. Okay. So that's the reason why stimulated emission is important. So we have thermodynamic equilibrium. It's a very simple balanced equation. Okay. Like your heat loss equal to heat gain, if you learn in PU and other thing. That's what he was trying to find. Energy, on both sides will be the same. So this is a very simple balanced equation. Nm into Amn plus Nm into Dnm into epsilon, Nm Dnm into energy absorbed equal to energy emitted. You can't emit more than you can absorb. Thermodynamic equilibrium. And of course, Mr. Boltzmann already has told you Nm by Nm is exponential minus h mu by kT. See, normally you have more in the lower level, higher level than in the higher level means lower number of electrons. Okay, lower level always has more. This is quite a common phenomenon. See, there are very few rich people, right, compared to poor people. Many more poor. Okay, this is again Boltzmann kind of thing. So you can say that for Boltzmann statistics, the number of atoms or electrons having 6 times the mean energy is only 1%. You can see from the exponential. Okay, so you can say the number of people are 10 times richer than the average, probably 1%. Okay, so they are told that 1% of the people control half the wealth. Okay, these 20,000 crores and whatnot. Same thing is also true in the US and other things. So again, the distribution is like that. So you expect many more in the lower energy than in the higher energy. So you have to stimulate them from the lower to the higher level. Like how you give loans to people to write, you stimulate them to higher level. So here again, we have to have external radiation to stimulate them to a higher energy. So that now they will part with their wealth. They will part with the what they acquired, and that is available. Okay, that's what is happening. So this kind of analysis can be extended to economics also. In fact, 3 years back I gave a talk here on applying physics to principle of physics to economics. So I discussed some of these ideas which are in fact being used in economic models. Okay. So anyway, that's understood. Again follows from maths, probability and other things. Okay. So this is a quite neat thing with Einstein. So he wrote that epsilon is Am and by simple algebra you get this. Comparison with Planck's law immediately gives you Am by this is how he derived the relation between the two coefficients, Am by Em. For atoms kept in a radiation field of intensity epsilon, the incident radiation will emerge from the atomic system with intensity. So if you excite them, if you excite more to the high energy level, Nm will be greater than Nm, so Nm minus Nm is epsilon Dm. Okay? So they all emit their radiation, this is the intensity. Okay? So it will be amplified if Nm is greater than Nm. So to amplify the incoming radiation, you must have more electrons in the higher energy level. The Nm should be greater than Nm. This is known as population inversion. Invert the population. Normally you expect more in the lower energy level. Now you invert it and induce more in the higher energy. Keep more in the higher energy level. So that they'll part with their radiation. Okay. Stimulation, they'll emit their radiation. Right? They're stimulated, they emit more radiation. So that's what happens. That's what we do in a laser. We pump the laser with external radiation, excite the more number of electrons to the higher energy state, more than in the lower energy state. So you'll get a net amplification. That's the idea behind the laser and laser. So we've got a 3-level system here. Of course, this is something about textbook stuff. I don't want to go into it much. So this is what you induced radiation is the same phase. So the important thing is the induced radiation is the same phase as the external radiation. Okay. And it's possible to produce from an input beam. So please note this, from an input beam of only several watts. Highly monochromatic, several megawatts per centimeter square can be produced. The outgoing radiation from after the stimulated emission can be several megawatts. In fact, some of the most powerful lasers now have emissions of petawatts. Okay. They had the Shiva laser some years back in the Lawrence River model. They had something like 3 terawatts. Okay. It's called Shiva not because of the Indian was made in India. It's because Shiva's third eye, very powerful. Open the third eye and have it. Okay. So the Shiva laser was the most powerful laser, 3 terawatts. Okay. And the name after Shiva. Now the Nova laser was there later, 100 times more powerful. Now we got lasers of about petawatt and exawatt. That is 18 watts. Okay. Tremendously powerful laser. Can heat matter to millions of degrees. can compress matter. Light exerts pressure. It can compress to millions of atmospheres. Okay. All this we try to. We want to have this same kind of nuclear reaction will take place inside the sun. So we can use our ordinary hydrogen and heavy hydrogen, the oceans to produce energy, fusion reactions. So of course, the long way off, maybe not before 2030. So anyway, people are trying powerful lasers. Okay. So we see so many applications. So we got a 3-level system. That's what happens here. Yeah, I won't go into the details because this is the whole idea. You pump, you create a population inversion, you stimulate the higher energy electrons with higher energy level to emit their radiation. By the incoming beam induces it. Okay. So that's what you do. So light from the pump of energy EP excites the transition state 2, that's the earlier figure. So N2 atoms in state 2, atoms at level 2 can emit in transition 2 to 1 or 2 to 3. Atoms at level 1 can emit 1 to 3. So with suitable values of Einstein coefficient, possible to achieve the condition. So suitably choose the material with Einstein coefficient to get N2 greater than N1 for amplifying light of frequency E2 minus E1. So that's how the laser works. So laser beam is highly monochromatic, very small bandwidth, highly monochromatic, concentrated over around a frequency. So the intensity of laser beam is very high, much higher than sunlight, billions of times more intense than sunlight. So you can see a laser beam, even a 10 kilowatt laser beam, you can see it over 10 light years in an ordinary telescope. So in fact, what they did was they did an experiment, and I just mentioned it. They used the most powerful laser beam, I told you, the Nova laser. They focused it through the Keck telescope, the world's biggest 10-meter telescope. So it could, in principle, be seen over 1,000 light years. So suppose there are some advanced civilizations who are happening to be in the right, seeing in the right direction, they can detect this laser. Okay, and know that we expect that maybe there are other intelligent within our testing advanced civilization. They will develop lasers. Easy way of locating them because their lasers will be very powerful. Okay. Already astronomers are interested in this kind of thing. There are many projects to look for these kind of signals. So I just mentioned in passing. So lasers, there are no limits to their application. So this is the difference between a laser. A bulb is a very incoherent emission, random emission of photon, whereas the laser is highly collimated. Planned, you accept all the most of the electrons to higher levels, it gives them emission. So it occurs randomly with spontaneous, otherwise it is stimulated not coherent. That's why the bulb on the left side. And then you have the laser here is highly coherent and very intense. Beam is very intense. So that's the difference. So the laser atoms are first popped to an excited state and then stimulated to emit photons by collision of photon. There was the same energy. Okay. We need a photon of the same energy as the transition. So in popular university, majority of the relevant entities are excited. Okay. So the majority are, so intensities are, okay, let's see. In a laser, atoms are pumped to the excited state and then stimulated to emit photons by collision with photons of the same energy. In popular immersion, majority of the relevant entities are excited. This can be achieved by special pumping, as I told you. And the pumping can be even with reactions. We have got very powerful chemical lasers, such as discharge gases, recombination emission semiconductors. We have got semiconductors. In fact, this is an example of a diode laser, small lasers. Okay, these kind of things. So of course one can write big books on lasers and all that, they're already there. Okay. Anyway, I just mentioned the importance of the Einstein A and B particles. It doesn't stop there. We also have radio. In fact, there's something called Mason. Okay. The first laser was developed by Theodore Maiman in 1960, the Ruby laser. It was the Hughes laboratories, and here the radiation is diffused along the reflected back and forth along its path by a mirror. We saw in the figure earlier. At one end and partially transmitting mirror at the other end. Between mirrors, the waves are amplified by stimulated emission. Radiation emerges through a semi-transparent mirror at one end as a positive coherent field. Okay. That's what is achieved. And many applications of lasers, welding, surgery, cooling, heating, printing, communication, reading digital information, so on. You can list hundreds of things. And laser preceded the laser. What is laser? Microwave application. In fact, the ammonia laser was developed by Charles Towns. In fact, Towns shared the Nobel Prize with two Russians, Prof and Astro. It was independently developed in Russia by two Russians. So Towns was the pioneer in lasers. And the laser radiation, again, the same thing happened. So the frequencies of the radiation are the microwave range rather than optical or ultraviolet. So, and now it's all, lasers are important in space also. Radio astronomers have been, I just mentioned this in passing, radio astronomers now routinely study naturally occurring cosmic laser sources. Einstein coefficient is also widely used in understanding stellar spectra. Even spectra from stars that we understood with Einstein. It's not, not just application to lasers and to terrestrial atoms or molecules. Very important for stellar and other spectra. In cosmic lasers, what is called cosmic laser, intensities of certain spectral lines are greatly amplified. Okay. By laser action to produce intense source of radio emission. First laser identified was the white hydroxyl. The hydroxyl on the ground is very unstable. It quickly combines the hydrogen to form water. Hydroxyl in space is stable because it is very rarified. They take a long time to collect. So OH is available as a radical. Present. So OH laser is there. It was seen at 1665 megahertz in 1965. That's important in cosmic laser. So cosmic laser emission now known from many other molecules, including water. We got water lasers, methanol lasers, ammonia lasers, HCN lasers. 30 different laser lines of SiO, silicon oxide, were observed in circumstellar node. The particular star we like Canis Majoris. Interstellar lasers are there. So lasers are occurring in space also. Okay, very powerful lasers. So Mr. Einstein's influence extends over also to very high, great distances also. So mega lasers are the extremely powerful lasers in active galactic nuclei, millions of times more powerful than in our galaxy. Okay. Most powerful are the OH and H2 lasers, generate millions of times the sun's power. Okay, 10 to the factor of watts. Same thing is happening there. On the ground state, they accelerate to a higher level by the background radiation, and then they release their coherence of their emission. You get this message. Okay. So lasers are there. SiO lasers are there close to red giant stars. People can see. So A and B Einstein coefficients are essential in understanding all these phenomena. You cannot understand all these phenomena without using Einstein. So you see the largeness of this subject. So I think with this I will go to the next, third topic in the trilogy. Okay. This is the cosmological constant. So Einstein was not particularly happy with this afterwards. A and B, of course, was okay. Gravitational waves. See, what he felt about gravitational waves was, he realized they were very weak. In fact, he was very pessimistic. He said, I think they'll never be found. He was half correct because it took 100 years until directly verified. So he himself was very doubtful. He said, I've written all the formula and all, I don't think he'll ever be observed. Okay. And A and B, of course, he was not fully satisfied because the correct picture came only with Bose. In fact, Bose, the story is when he wrote the paper giving an alternative derivation of Planck's law using a new statistic, Bose statistic. In fact, he was not sure of the. He sent it to a number of journals, all rejected. The English journals, all rejected. Because of the fact desperation is sent to Einstein. The note saying that respected sir, you have a look. Einstein had a look. He said it's very important. In my view, it's a very important contribution. He added translated himself with Japan and got it finished. And Bose didn't do anything much after that. Then Einstein thought more about it. He said, oh, it predicts a new phenomenon. Atoms or any entities obeying this statistics can all be mostly in the ground state. They can occupy the lowest possible state, leads to highly condensed state. So he was good enough to call it Bose-Einstein condensation. Okay. So although it was his contribution. So it was 1926, 10 years after this. So a scientist in his late 40s can make very important contribution against him. And even more important, equally important contribution was the Einstein, the ESP, so-called ESP paradox. It became a very important contribution for EPR paradox, Einstein-Podolsky-Rosen paradox. So he raised several issues in quantum mechanics. In fact, this became very important later with the work of Bell and Brooks, understanding the formulae of quantum mechanics. This was 10 years later, 1930. Another. So Einstein continued to make a lot of contributions till the end. Okay, and so this is another. So he also introduced what's called cosmological constant. Okay. So how did this come about? The famous lambda term, why and how. He got it the lambda term. Lambda is the Greek letter, the capital form of lambda. Lambda, you know, for wavelength you use the small lambda. Physics you use wavelength. This is the capital lambda. Okay. He called it lambda. So it became known as the lambda term. Why and how. So you see why and how. So on February 4th, 1917. So he had this idea already in 1916. He formalized it in February 4, 1917. So Einstein wrote to Ehrenfest. Ehrenfest is another well-known scientist. And he quoted in the book, Invented Universe by, Eckersberg, 1908, What did he say? This is what Einstein said. I have again perpetrated something about gravitational theory, which somewhat exposes me to the danger of being confined to a madhouse. Okay. Because he had a very radical idea. Okay. He revealed these maddening thoughts 4 days later to the Royal Prussian Academy of Science. So that time he was associated with the Prussian Academy of Science. He was one of the members. And he published a week later by the Academy. Okay. And thus began modern relativistic cosmology. So thus began cosmology, the study of the universe as a whole. Nobody had earlier dared to study these things mathematically. So Einstein, with this term, started this whole process of relativistic cosmology. Okay. So this is the 100th year of that. Okay. So this again proved to be a very important thing, as we shall see. Why and what did Einstein introduce? Spurred by the success of, by the time the general theory of relativity had there are 3 tests. He could explain the perihelion of Mercury. Newton's theory failed to explain why Mercury's perihelion advances by 40 hours per stage. The observations were very accurate. The very good astronomers who have made very precise observations. People like Leverrier, the French astronomer, Newcomb, the American astronomer. They had found that Mercury didn't behave according to Newton's law. There's the nearest point rotated around the sun. There's a deficit of 43 hours per stage. So, what is the reason? They even thought there's a planet between Mercury and the sun, giving an extra pull on Mercury. But nobody found the planet. Okay. But Einstein's theory correctly explained he had an extra term compared to Newton, that correctly explained. And the deflection of light was twice that in Newton's theory, that was verified later. And the gravitational redshift. So all these things turned out to be correct. So he thought now he was very spurred by these successes. He was even talked about as a new Newton, okay, very revolutionary kind of thing. He said, now why don't I apply this to cosmology? Why don't I apply my theory to cosmology? That's how it started. So you see, he had his so-called field, we don't worry much about it. He had his usual, the famous general relativity field equations. Okay. First he didn't have this term at all. He wrote 40 papers with just these 2 terms, which are wrong. Okay. He wrote 40 wrong papers. So coming to the right equation. He wrote many of them with his mathematician friend Grossman. Okay. Grossman was a mathematician friend. See, if you see the special theory of relativity, he doesn't require much of mathematics. It's more of algebra. But for general theory, he had to study, tensor analysis, differential geometry. So he got the help of his mathematician friend Grossman. He was his classmate, but in mathematics. So he took the help of Grossman. Together, set up the equation of general relativity. They worked with the wrong equation for quite some time. Okay. Then it was corrected later. So then he wrote the final equations, and then he wanted to apply it to the whole universe. But then he made a strange assumption. He made a wrong assumption. The universe should be static and unchanging. This is more of a philosophical prejudice. Because philosophers are always interested in the universe doesn't change in time, always the same, always been there, always will exist. So it's eternal, So he thought it should be eternal. Nothing is changing. So whether mathematically you want to show whether the equation gives that kind. So the first assumption. Not surprisingly he found, why surprisingly he found that the equation do not admit a static solution. They don't admit, there is no static solution. See, gravity is described by general relativity, gives a large scale attraction. Okay. Gives a large scale attraction. This even Newton knew, okay, pulling everything together. If you just have gravity, everything will be pulled together, right? Any two bodies attract each other. They can't be static. They just can't be static. Okay. So not surprisingly, he didn't have a static solution to the equations. Unless he found he should add a term to make it static. Okay. And that's why he added a new term, lambda dv. Lambda is a constant which he introduced. Dv is the uniform distance. So this is a new equation equal. This is extra term. Okay. This gave us static. So what does the lambda term do? Basically, it introduces a large scale repulsive factor. Now you know gravity is attractive. Now you know the elementary problem in physics. If you want static equilibrium, you have to balance the force. You want attractive force, you must get the repulsive force to balance it, to give a static configuration. So that's what he was trying to do. So the lambda term introduces a large scale repulsion, lambda r square, increasing with distance, lambda r square, to balance the attraction. So he got the equilibrium size or radius for the static universe. This is called the Einstein universe. RU is 1 over root 9. This became known as the Einstein universe. Sometime in 1917 he gave this idea. Okay. He started in 1916, 1917 he had given the solution. It's called the Einstein universe. Okay. Lambda is the universe of curvature, okay, the beta minus 2, and this became known as Einstein's static universe. Static. He estimated the radius as few billion light years. It was very consistent with what was known that time. So he was very happy about it. He was quite happy about it. Okay. However, a few years later, Mr. Hubble was given charge of the 100-inch Mount Wilson telescope. That was the world's largest telescope that time, in 1918. Then he observed that all faraway galaxies show a redshift proportional distance. They are all moving away from us, not coming toward. They are all moving away. Velocity proportional to r. Looks as though all the galaxies are fleeing away from us. Everything is expanding with everything else, with respect to everything else. So this suggests the universe is expanding, not a static universe. Okay. This was the so 10 years after Hubble started observing, the general consensus was the universe is not static, it is expanding. Okay. So this Einstein now was not very pleased with this. This is Mr. Hubble making his observation. Edwin Hubble is making his observation with the 100-inch Mount Wilson telescope, the world's largest telescope at that time. Only the Palomar 200-inch came 30-40 years later. Okay. So that time is so he uses to observe stars in many of the galaxies. Okay, and he found they are all showing a redshift. They are moving away. Wavelength is increasing with rather than decreasing, rather than being the same. Increased wavelength means is moving away. Wave is stretching. So it's called the redshift. Okay, so that's the discovery. Okay. So all this observation definitely suggested an expanding universe. 10 years observation, not 1 year, 10 years, but a 10 years observation, we concluded, okay, that it is expanding. And with time, and not a static one. So the weight of evidence increasing by expansion, Einstein realized he could have predicted a dynamic universe. Suppose he had not introduced lambda, he could have predicted the universe is not static, right? He could have predicted it is expanding, okay, dynamic. So he said, oh, I shouldn't have introduced it. I missed a prediction. Okay, he gave a wrong prediction. It's static. So he remarked later, maybe in a letter to Gamow, that it was probably the biggest blunder. Introducing such a term, arbitrary term. It's an arbitrary term, right? So he didn't have to introduce it because he had the prejudice it should be static, philosophical prejudice. And then Hubble's observation showed it is expanding. So he said, I should not introduce a big blunder. Okay. So he left it at that. And what happened? A big blunder. It's a famous Einstein putting out his tongue. That he's cynical about many things. Later on in his life. Okay. However, in terms of introduction of the term was not his real blunder. It was not the real blunder. Of course, people can introduce terms, nothing wrong. People have introduced a lot of terms for other things. What was the real blunder? The bigger blunders are not realizing that a static universe results only when there is no matter. This is clear even from Newtonian theory, because r the rate of change of the scale factor of the universe, r dot by r is proportionally 8 by 0. If you want a static universe, r dot is 0, that is the change with time is 0 of the so-called scale factor, or you can say size of the universe crudely. Only when rho equal to 0, you can see that r dot is 0. So the static universe is possible only when there is no matter. Okay, when there is no matter. So that is the first mistake. This even Newton knew. So only Einstein did not read properly the Newtonian thing. Okay. What is the second blunder? Second blunder was he thought he has got a stable static configuration. of balancing the attractive overall gravity with the lambda reflection, thus getting a balancing radius. But you see, we know even in elementary physics, if you say something in equilibrium, you have to test it whether it's stable or not. Okay. If you watch laser equilibrium about a point, something is oscillating. You want to know whether it's stable or not, what do you do? You perturb it around this equilibrium point and see whether the oscillations are stable. Okay, that's what you do. Okay. You take the first derivative with the second derivative, you take only with positive, it's stable, right? It's a very elementary thing. He didn't realize it. It's very surprising, right? However, it's an elementary problem in physics to check whether the equilibrium around a position is stable or unstable by making small perturbations above the equilibrium coordinate. Einstein did not check for this. An elementary calculation, first point out by Eddington, one of the great physicists, shows that the Einstein universe is unstable to perturbations. It could either blow apart or collapse to zero degrees. Surprisingly, Einstein did not realize this. So although he made much of his starting universe, it is unstable. Okay, small perturbation will collapse. It's an easy calculation. Why didn't he do it? He was the greatest physicist of the time. So he was too much in a hurry to say it is okay. Another problem. This is a more bigger problem because there's a small problem in equilibrium. Then one more problem. What is worse? He insisted that the Newtonian limit of his extended field equation to the lambda term is given by the modified Poisson. If you don't understand, you don't have to worry. If he takes the limit to Newton, there is a weak limit, weak field limit. The Einstein theory holds for strong gravitational field. If he goes to the weak field limit, he will get this. That's what he found. This is the real blunder. So this is the real blunder. This is not the correct, even mathematically it is not the correct. Mathematically this term is wrong. Okay, mathematically. So this is the real blunder. Opening line in a bizarre comedy of errors. So Einstein modified Poisson equation, a modified Poisson equation would give rise to potential e to the minus kr by r, falling off with r exponential. Rather than, see, we said that lambda gave lambda r square repulsion, right? But this equation will give you e to the minus kr by r, falling off exponential. Okay, something like the Yukawa potential in nuclear physics. Okay, so obviously not correct. So Einstein modified equation, Poisson equation, is familiar to all physicists through the Yukawa meson theory, which has a spherically symmetric solution. Okay, this is constant, e to the minus, it drops off. That's why nuclear forces are short range. You don't feel the forces beyond the nucleus. Okay, nucleus holds the protons and neutrons together, but it's not felt over a large distance like electromagnetic gravitation because it drops off exponentially. That's the equation. It was written as the Yukawa equation. Okay. Now the context of Newtonian gravitation, such a modification empirically introduced by Seelig and Newman around 1900. In fact, this kind of term was introduced by Seelig and Newman around 1900, much before Einstein theory of relativity, to include the exponential cutoff of the potential, trying to explain Mercury's. They are trying to explain Mercury's anomalous thing by modifying the Newtonian potential. They had a term like this, but Einstein was not aware of this. Although he wrote this paper in 1917, you are not aware of the work of 1900 of Seelig and Newman. Okay, you are not aware of the work. But that's not the problem. If you are not aware, that's not the problem. So it is true that the Poisson equation modified by a term minus lambda gives rise to an exponential cutoff for the gravitational potential. But Einstein flagged the assertion that the lambda term in the modified field equation has an analogous effect leads to a lambda phi term is completely wrong. Okay, it's completely wrong. He didn't realize it. Okay. So the correct Newtonian analog, this is the correct term. This now, I think those who know a little bit of differential equations can verify that this gives the correct repulsive force lambda r square. To solve this equation, you get lambda r square increasing with r. This is what Einstein intended earlier. You want a repulsive term to overcome the gravity. Okay? So the correct form is this, not the one earlier. Okay. However, this is the important point to note. However, generations of physicists, even relativity specialists, have repeatedly parroted this nonsense. Okay. of the lambda phi term rather than the correct lambda 3 term. Where I wrote some papers in 94 and pointing out these. So some eminent recent examples. What are some eminent recent examples? Making the same mistake. One is Abraham Pius. In fact, I don't know whether you have read the biography of Einstein written by Subtle is the Lord. That's the title. Because one of Einstein's famous quotations is, "The Lord is subtle, not malicious." Okay. He said God is not malicious, but he is very subtle. He doesn't want us to know the law already. But he is not being magic. Ultimately, he enables us to know. So the title of Abraham Pius' book is Subtle is the Law. Abraham Pius is himself a famous physicist, particle physicist. He wrote papers with Sheldon and Pius on K0 generation and so many things. So he wrote a magistrate biography of Einstein. And what does he say? About the analogy between lambda and Poisson and he gives the same exponential cutoff. Then even Stephen Hawking makes the same mistake. Hawking is supposedly new modern Einstein. But in a 1983 Royal Society discussion, 1983, he begins by saying Einstein lambda term modifies Poisson given exponentially falling human type. And J. Weber, I told you the picture of Weber, gravitational waves. So he's trying to have gravitational waves with the lambda kind of thing. He also says you have got the same kind of thing. Okay. Yeah. So Weber also makes the same mistake. Okay. In a 1989 paper. Okay. The same kind of mistake. So you see, this is what. Thus the lambda term includes the force mc square lambda by 3 root r. Okay. A force analogous to the repulsive oscillator potential. Oscillators have a potential kr square. Okay. What happens? This is the correct potential. A force increases with distance rather than exponentially decrease. Eddington clearly showed this, and one of the few who did not blunder. Eddington correctly gave the picture in 1923. In his book Mathematical Theory. He was one of the few who gave the correct picture. So instead of getting a shielded gravity field, one has now at large distance almost naked to quite different from Einstein's expected path. Okay. Incidentally, in fact, there were also mistakes in Einstein's earlier, even in the 4 great papers he wrote, some of them are mistakes. So in fact, one person called H.C. Ohanian, I don't know whether you heard the name, is himself a well-known racist, Ohanian. He wrote a massive book, Einstein Mistakes. He produced a book in fact, Einstein Mistakes. And the mistakes that he pointed out in the lambda are not there in his book. He has missed them. He has pointed out several other mistakes, but he has missed these mistakes. So this is a lesson to some of you. I hardly see any young people in the audience. All are mature people and so the message to younger people is read the things carefully. Read all your books, everything carefully. There may be certain things which are not okay. Even Einstein can make errors. So read your things carefully. Okay. Ask questions, read things carefully. This will include the motto of this festival, which says question mark. Okay. So just read it. Don't read the textbook as all Bible. Okay. Do report for new ideas. Hardly I don't see any youngsters, so very few, no? It's true in all maybe the timing is 6 o'clock, 9 o'clock, gone from college, they want to rest or go to the mall or relax. So anyway, so this is the thing. So anyway, I am almost ending now. So what is the modern irony? I told you Einstein said it's the biggest data. He was no longer interested. He was no longer interested in the lambda. Okay, he said it should be valued. But he is like genie in a bottle. Once you release, then he is very difficult to read that. He continues to hunt. Okay, so something like that. So what is the modern irony? The modern irony is this large-scale lambda reflection. First example of dark energy. Making the universe expand faster and faster. See, a repulsion will make the universe expand faster and faster. Okay. Now suppose I throw a stone up, it falls down, right? Because the Earth's gravity is pretty strong. So once people realize the universe is expanding, that's the correct picture. Will the expansion stop after some time? Will it slow down or will it expand forever? Then people thought, many astronomers, most astronomers thought, and cosmologists thought, the combined gravity of everything will pull it back. So the universe should slow down, should decelerate. Okay. But the surprise of the past 15 years is that the universe is actually accelerating. The observation shows it's expanding faster. That means there's some kind of repulsion, large scale repulsion. Okay. This is called dark energy. So dark energy is a state of matter which has negative pressure and makes the universe expand faster. Okay. And the Einstein lambda term is the first example of that. Okay. Of this dark energy. Einstein didn't call it that, but it's a repulsion, large scale repulsion, and it will give rise to an expanding universe expanding faster. Okay. Ironically, this is the punchline. Ironically, many of the recent observations are consistent with the lambda term. They're consistent with Einstein's cosmic constant dominating the universe to the extent of 70% of it. So 70% of the dynamics of the universe is governed by Einstein lambda term. What he said is bigger than that. Okay. So many editorials in famous journals like Nature, they say what Einstein jumped may be now the thing which is driving the universe. Okay. So we are back now to the point. So we're back now to the Einstein kind of picture. See, Einstein used the lambda term to get a static universe. Already in 1917, hardly 1 year afterward, this made nonsense of Einstein's static universe. Okay, De Sitter is another famous Dutch mathematician. It's called the De Sitter solution. Einstein static universe, the lambda term, by finding an exact exponentially expanding solution for a universe with only a lambda term and no matter. So Einstein, De Sitter said, let me see what solution I get if I have only a lambda term and no matter. Okay, no other matter. He got an exponentially expanding universe, opposite of Einstein's static universe. He already made nonsense of Einstein's static. Okay. So in fact, Einstein was angry with De Sitter. He said the universe is not physically relevant because no matter is there. There should be matter. So people joked Einstein universe has matter but no motion. De Sitter universe has motion, no matter. So we need something, some combination. Okay. So this is already made, made the thing quite. And this is also evident from R dot bias equal to constant. Lambda term is a constant. If you solve this, you will get exponential expand. Very simple calculation. There are students, I hardly see any younger people, they can work it out. It's only a little bit of the BSc calculation. Okay. This was immediately after Einstein's paper. The De Sitter solution immediately. In fact, the De Sitter solution formed the seminal basis for modern inflationary universe. See, Big Bang universe has so many problems. What came before the, in a very early time? How did the universe start expanding in the first place? See, gravity should make everything collapse. Why did the universe start expanding in the first place? You need something like a lambda term. So people have brought it back now. This is called the inflation picture. Okay. So you need something like Einstein lambda term, but a very large one. See, Einstein lambda term is very small. You need a very large one to make the universe expand very fast. So this is the inflation model. So ironically, he uses the De Sitter solution. De Sitter solution is just a solution of the inflation model. So modern hindsight. What is the modern hindsight? The introduction of lambda amounts to a redefinition of the vacuum state for the universe. The vacuum is a very complicated quantum theory. You have to redefine the vacuum according to the coordinate system. You replace the Minkowski vacuum. Minkowski system is flat spacetime. Sorry, the flat Euclidean with De Sitter spacetime. Okay, De Sitter spacetime is an example of a vacuum. It is no matter, but it is vacuum. Okay, it is pure vacuum. So vacuum drives the universe. Okay, there's the quantum vacuum. Okay, so this is the point. So the lambda term introduces the negative pressure with the equational state T minus rho c square. Negative pressure gives rise to repulsion. You can easily show this, not difficult to show this. Okay, this is again BSc maths. In a more external course, I sometimes give these derivations. Okay. So dark energy dominating the universe at present, accelerating universe. In fact, the people who showed the universe accelerating from observation got the Nobel Prize in 2011. 3 people got the Nobel Prize in 2011 for showing the universe is accelerating. They didn't tell what is accelerating it. They didn't say it's Einstein lambda term. proof, observational proof, the universe is expanding faster now than what it was 8 billion years ago. Okay, observational proof. So 3 of them were the Nobel Prize. So you see the important discovery. And the latest observations show that the dark energy may well be Einstein's cosmological constant. Okay, so we have so now people write it as P is minus W rho C square, and W equal to 1 gives your cosmological constant. W equal to 1. Recent current observations suggest W is close to 1. Einstein may turn into this gray. It's because Brunner is now dominating the universe. May turn into this gray. What is happening? The same year, gravitational waves have been discovered. Einstein lambda term is dominating. What after century that we have come back to. That's the interesting part. If in the future, suppose in the future, people have plans to launch a dark energy probe in space. Dark energy is confirmed to be just a cosmic constant. Einstein should get 2 posthumous Nobel Prizes. Because they don't give Nobel Prize posthumously. One for gravitational wave prediction, other for the cosmological constant. Both in 1960. Okay. The only Nobel Prize that are given posthumously is for peace to one Dag Hammarskjöld. You know how many people have heard. He was the second UN Secretary General. First was Trilogy. And you know who the present Secretary General is? That team. Okay. And so Dag Hammarskjöld was the second Secretary, UN Secretary General. He tried to arrest the conflict in Congo. There was again a fight between the proxy war between the US and Russia. Okay. So what happened was when he went to negotiate the peace, his plane was shot over the Congo. He died. So that year, a few months later, they awarded the Nobel Prize in Peace, posthumously, 1961. The only example of posthumous Nobel Prize. Although some people have, there are 2-3 cases where people have died after the announcement. But it's okay. But they are alive when they were given the prize. That's the condition. And offered the prize, they will be alive. So only the case of Dag Hammarskjöld, they made an exception. So whether they make an exception for Einstein, we don't know. And we don't know who will correct it because all these people have died. Some everybody is no longer there. We don't know who will correct it. So anyway, both the things are, although he felt the biggest blunder is there, but it's ironic because the blunder gets. So that's how. So now we know that dark energy dominates the universe by measuring the deceleration parameters. That's what people have. So whether the universe is slowing down or expected or expanding faster. The last answer. So this is a little technical. How do we know the universe is expanding faster? All these formulae are there. So it turns out that the parameter is negative. If it's negative, that means it's actually. Okay. They showed it minus 0.58. So this together with the total omega 1 gives you predict the dark energy dominance. Okay. It's a little bit of calculation and other things. This is a modern kind of thing. So astronomers are to check and retake. I'll go to the next one. So Einstein lambda may also explain why the universe started expanding in the first place. Because gravity should have made it collapse instantly. It should have expanded, it should have collapsed instantly. Why did it start expanding? So a large cosmic vacuum and a vacuum term predicted in modern theories, unified theories, is equivalent to a very large lambda term in the early universe, making the universe expand exponentially in the day. What happens? The vacuum energy undergoes a change. The early universe, like latent heat, See, latent heat is released when water completely boils, right? Similarly, melting. So here there's something similar, vacuum energy is something similar here, like latent heat is released. Okay, this drives the expansion of the universe. Okay. Because the energy, any energy can drive the expansion. So to put it in familiar terms, that's how it works. Okay. So the very large lambda term in the early universe, making the universe expand exponentially in the beginning, just like Mr. Disitter said. So negative pressure would create matter, so the total energy is zero. So it turns out negative pressure can create matter. Okay. Because if something in negative pressure expands, more and more volume is created, more and more negative energy. To compensate for that, you create positive energy particles, so the total energy is zero. So the tradition of the inflation model is total energy universe is zero. Okay. This is also borne out by some recent observations. Okay. Gravity and the restaurant cancel each other. Okay. So it's an example of creation ex nihilo, from nothing. Creation from nothing. Okay. This is also called, so one of the people who proposed this is because the free lunch. Okay. See, the Americans who introduced this happened, right? So there is no such thing as a free lunch. So according to them, you have to work for your lunch. Okay, you can't eat unlike our kind of thing. But there also many people get food stamps. Those who are not employed get free lunch. Can exchange coupons. Currently 100 million coupons are being exchanged every day. Okay, so there also there kind of free lunches are there. But anyway, this is a statement. There is a free lunch. Okay, it's not created from nothing. Okay, just like a fluctuation produced with total energy zero. So how did such a large vacuum energy drop? A time-varying lambda, a time-varying cosmological constant, very large, the beginning now very small. This is called the quintessence picture. So people are now working on all these things. Hot topic. A lot of fine-tuning is involved. Okay. We have to explain why the vacuum energy density comparable to matter density. Why are the two comparable now? Why is vacuum energy similar to the matter energy now? Answers to old problems raises new problems. There is no answer. Lots of things remain to be understood. So if there are younger people here, there are lots of new things to do. Okay, I don't know how many are explained. Okay, the end of physics is certainly not there. A lot of new things are there to be done. So this is the final ending. Einstein neither liked lambda nor the then formulation of quantum theory. He is unhappy with the lambda term. He is unhappy with the Copenhagen formulation of quantum theory. He said, I don't believe God plays dice. Not everything is probable. Okay. So you're not happy with the formulation of quantum theory. Of Heisenberg, Schrodinger, Born, and he simply says, I don't believe God plays dice with the world. Okay. But ironically now we believe that quantum fluctuations, quantum vacuum energy should generate a lambda term. How do you generate a cosmological constant? By quantum vacuum energy. Okay. Quantum field theory predicts a vacuum energy which will generate a lambda term. Okay. And perhaps even Einstein's gravity can be generated by quantum vacuum fluctuations. It's called violation of scaling physics. So ironically, everything can come from quantum physics. Okay. So this will really make Einstein even more troubled. Okay. So with this, I think I will stop.
Ladies and gentlemen, it's our fortune to have heard a wonderful talk on Einstein Trilogy, gravitational waves, A and B coefficients, and cosmological constant. It has been very informative and interesting talk, sir. On behalf of Bangalore Science Forum and all of us here, I propose vote of thank you, Dr. Tomorrow talk by Dr. S.S. Srikanta, Medical Director and Senior Consultant, will be speaking on beta cells, insulin, diabetes, immortality, and human spirit. All are cordially invited. Any questions?
Sir, when we look at the constants, the lambda c square, does that mean that does it mean that actually the repulsive force is greater than the attractive force or the gravitational force? Because the Einstein originally considered the idea that it was an weak field and to balance an attractive force. So does this equation mean that the repulsive force is actually greater in present day scenario of equations? So as to say that the universe is expanding, accelerating.
No, it doesn't tell you that at all. Because it depends on the value of the lambda term, right? Depends on it gives you the solution, that's all. So whether it's more or less now depends on the value of the lambda term. So the thing is, it has been observed the universe is accelerating faster now, which means the lambda term is dominating. The matter, because corresponding to the lambda terms is the density lambda c square by 8 by g. Okay, g is the gravitational Newtonian constant. So if this is more than the matter density, the universe is accelerating.
So since the lambda is greater, the assumption of Einstein from where he made the lambda to be under the weak field, but this doesn't give the same value, right, sir?
Yeah, he wanted to match with Newton's theory, okay, because the lower limit, see now everything is now, since the universe has expanded so much, all the quantities are of quite low values. So the weak field is quite okay now. Okay. Whereas if you go to the early universe, the weak field will be a very strong field. Okay. There will be difference. And the lambda term was not important in the early universe. The matter density was much more. It was much smaller. Actually, the total term, see the Poisson equation, you got del square phi, 4 pi g rho and lambda c square. So 4 pi g rho was much greater than lambda in the early universe. Now in terms of lambda is more than 4 pi g rho. Because rho is dropping with time as the universe expands. But lambda remains more or less constant. Okay, right from the beginning.
And sir, regarding gravitational waves, does the gravitational waves means the end to the hypothetical particles such as gravitons?
Oh, graviton, you see, that comes the next step. You have to quantize the gravitational field. Just as they got classical electromagnetic field. Only if you quantize it, you will get the photons, right? Here the gravitational field has to be quantized. So just as you say that the force between two charged particles are mediated by photons, okay, in quantum theory. Here the force between two particles are mediated, gravitational force is mediated by gravitons. Okay, we can write down the equation for graviton, spin 2 particle. Then we spin 2. See, a photon is spin 1 particle, the graviton is spin 2. Because the description is of a second order tensor. In electromagnetism is a first order tensor vector. Okay, you know, we have 4 components of there of a vector. Gravitational field has got 10 components, so you need a second order tensor. Which means the spin 2 field. Okay. So graviton has spin 2, we can formally have the same kind of thing. But of course, to see gravitons requires a much more, see, it has taken 100 years to see gravitational waves. So actually detect gravitons will take probably another maybe several decades. Because the processes are very weak. Okay.
Are we looking at particle wave theory again, sir? In the aspects of gravitational fields, are we again looking at the particle wave phenomenon, gravitational waves and gravitons, simultaneously affecting the fundamental properties of any matter?
So gravitational waves are very, see, they are so weak, they will hardly affect any matter. I told you, suppose they impinge on any particular matter, they will hardly distort it by a small fraction. So they are so difficult to detect. See, recently they detected this gravitational wave. The Earth itself would have contracted only 1 nanometer. You can expand by 1 nanometer. It's very, very weak. But suppose, say, you got a very intense source of gravitational wave, maybe nearby there could be some effect, some absorption could be there. But all these sources are so far away, the effects are very, very weak. Okay. That's why it's so difficult to detect. You need very big detectors to detect even small.
Thank you very much. It was a wonderful lecture and discussion.